Okay, I agree. Let me just see if I can write here. Oh, I can write. That's good. Okay, so I was, as a word of introduction, I was kind of like puzzled how to talk to the audience here, who, as far as I'm concerned, deals mostly with sociophysics, and how to talk to you about fluid dynamics to make it a little bit appealing and interesting to you. So I hope that all those interceptions connected with galaxies and beaches and like holiday climates will appeal to you, and you will find this presentation pleasant. So to the matter of the subject, I'm going to talk about one of the numerical methods that is used for modeling fluid flow. So imagine that, for example, some big company, for example, Airbus, is preparing a project of a new airplane, and they want to calculate how much fuel it will burn, how much cargo it will be able to take on its into its fuselage. So they don't do it just like that. They need some tools, some numerical tools, some science to predict all those aerodynamic properties of a new plane design. And I would like to present to you one of the methods that may be used to perform such calculations of drag, of lift force of an airplane. That takes so-called mesoscopic approach, and it is based on statistical physics, on statistical approach to like multi-body system description. So this is the link that I think will connect your field of study and my field of study. So galaxy in a glass, modeling fluid flow with statistical physics. Let's see what we'll go through today. So at the beginning, a quick word of introduction. Why shall we be interested in mesoscopic approach to fluid description? What problems it solves, and what problems it poses. Next, we will see how this mesoscopic look at a fluid is obtained. Further, we will I will talk about one particular method to solve a governing equation. This is the method that I've just spoken about. It's called Lattice Boltzmann Method. And further, we will see a few applications and variations of this Lattice Boltzmann method to very, very wide variety of flows. And we will finish with a nice seashore sunset when I will summarize what I've presented today. So let's go to the introduction. So imagine you have a glass of water, yeah, and that was the first thing that I got to my mind when I was preparing this this seminar. How many molecules, how many agents? I perceive molecules as agents. How many of them are there in such a glass of water? So let's make some simple calculations. We know that molar mass of water is 18 grams per mole. So this gives something like 10 to the 22, 10 to the 23 particles in each gram. So if we're dealing with a full glass of water, which is approximately a quarter of a liter, we'll have as many as 10 to the 24, 10 to the 25 molecules in a glass. So as a comparison, it is estimated that Milky Way consists of about 10 to the power of 11 stars. So now imagine that we took each and every single star in the Milky Way and replace it with another Milky Way with this vast amount of stars. So this would give like 10 to the 22 stars. So this still wouldn't be enough to cover the number of water molecules in a simple glass. But somehow we have to calculate fluid dynamics. Yeah, maybe like pouring water to a glass is nothing spectacular, and no particular application may rise from it like instantly. But still, we are dealing with much more complex problems, much more sophisticated phenomena in those systems, and we have to calculate it somehow. So how to handle it? One possible approach would be to take so-called kinetic look at a fluid. So we know that, and rather we assume that fluid consists of some finite number of particles, and we say, okay, let's track position and, for example, velocity of each of those particles and see how they move through space, how they collide, and so on and so on. But still, 10 to 25 is a very, very large number, and I doubt if any computer is capable of like storing such large amount of data that would be needed for some real life and interesting application. Yeah, so on the other end of the scale, we have so-called macroscopic approach, which does not concern every single molecule separately, but it rather takes 2 steps back and looks at a fluid as a continuous medium. Yeah, so we are not talking about, for example, positions and velocities of those particles, but rather velocities of small portions of fluids, densities of small portions of fluids, and, for example, pressures that a fluid impacts the walls and other obstacles that it comes across. Yeah, but this approach has a drawback in the form of kind of forgetting that microscale effects. And okay, it may be good to use Fluent to simulate, for example, airflow around plane or things like that. But when one wants to incorporate those microscale phenomena, like, for example, something connected with energy levels, for example, of atoms that constitute the fluid, it may be kind of difficult to incorporate them in that continuum approach. So perhaps somewhere in between kinetic theory and macroscopic theory, there lies some approach that combines the two. And it turns out that there is such an approach. This is called mesoscopic approach. Okay, so let's now take 1, not 2 steps back from looking at our particles in a fluid, and have a short glimpse at this mesoscopic way. So it is popular to derive governing equations of this approach directly from kinetic theory, or rather, like, think about mesoscopic approach as a probabilistic description of a set of particles that constitute the fluid. So let's take a look at kinetic approach at first. We can define, okay, we might have a box of n particles. Yeah, there's a box, we have particles. And to describe the energy of such a system, yeah, we might construct something that is called as Hamiltonian function of the system. Yeah, so we take momenta of each particle, yeah, that's associated with their kinetic energy, and positions of each particle. So this may account for example, energy of each particle that is placed in some force field, yeah, space-dependent force field, and doing some manipulations on all of those 2 times n variables, we obtain some kind of estimate of the system's energy. For example, when we have 2 particles moving with their velocities, having their masses, and let's assume they also have some electric charge. Yeah, we can construct Hamiltonian as sum of kinetic energies, and also additional term that concerns the energy of electric interaction between those two particles. Of course, to describe a larger number of particles in the system, we have to incorporate more and more of such terms in Hamiltonian, and it is very convenient to describe the state of such a system. Yeah, so by state I mean the combination of positions and momenta of all the particles as a state vector. Yeah, so this is very, very multi-dimensional vector that is constituted by momenta and positions of particles. And we might be interested how those positions and momenta evolve in time, because this is quite an interesting thing to know what happens in time in such a system. So we can make certain manipulations on the Hamiltonian to get temporal dependence, like temporal rate of change of each of those momenta and positions for every single particle. But once again, if we would like to simulate very large numbers of particles in the system, this still wouldn't be a convenient way to do it. So instead, one can make use of kind of walk around and not deal with momenta and positions and so on of every single particle, but to make use of probability distribution function. Such a probability distribution function tells us what is the probability of our system to achieve a state defined by some particular state vector. Yeah, so if we imagine that we have that multi-dimensional space, for example, 2 times n dimensional, so each state of a system, like particle 1 has position q1 and momentum p1 and so on for every particle, might be considered a vector pointing from the system's origin to some point that represents the system's state at a given moment of time. And once again, we might be probably interested how this probability distribution function that describes the system evolves in time. So here where Liouville equation comes into stage, and this is a kind of transport equation of this distribution function. Yeah, we have a temporal dependence here. We have some kind of advective transport or whatever. And this I might view as a counterpart of those two relations that concern Hamiltonian derivatives to obtain temporal change of particles' positions and momenta. But still, we have to sum those derivatives over all particles. So it's still not convenient for large numbers of bodies in the system. So what about if we now somehow squeezed the distribution function and reduced its dimensionality? What I mean by it, we might be interested in a distribution function that as an argument does not take all of the momenta and positions of particles in the system, but only some particular ones, like smaller subset. Yeah. In order to do that, we might integrate that multidimensional function with respect to dimensions that correspond to some subset of particles. So let's say that we, for example, have 5 particles in our system, and we say, okay, we forget about certain properties, certain features of the last 2 particles. This is that part that we integrate with respect to, and we are concerned only with distributions of the left 3 particles. Yeah, so we are asking what is the probability of a system to achieve a state of those 3 particles concerning all possible states that those 2 reduced particles may achieve. And doing it for all the particles subsequently and performing some kind of truncation, some kind of linearization of the resultant function, we might arrive at a n particle distribution function, which depends only on spatial coordinates, velocity coordinates, and time. And it kind of incorporates all the particles in the system inside of it. Yeah, so this looks quite nice. This looks more convenient than dealing with all the particles.
Dawid, sorry, can I interrupt you for a while?
Yeah.
But if you
Shall I go faster?
Yeah,
Okay.
If you are doing this procedure, usually, probably in reality, you're taking each second or each fifth or something particle into the consideration, not that you delete last 5, let's say, and take the first. So like you are making some grain course description, or not really? I mean, if you, I'm asking if you are doing, in reality, you are doing something like this kind of, I will not maybe use randomization group approach because I don't know if you are familiar with, but if you have many particles, you don't delete really the last 3 of them, let's say, but let's say every second particle. This is what you are doing in reality or not really?
As far as I understand this approach, it's like reducing every single particle in subsequent steps. Yeah, like integrating.
Yes, I know, but the procedure how you are doing this. But okay, we will go to this
Okay, maybe after the presentation. Okay, so to speed the things up, we are interested how this like distribution function describing the whole system evolves in time once again. Yeah, so an equation that describes that temporal evolution is called Boltzmann transport equation. Yeah, so here F is that overall, let's say, distribution function that describes the whole system, not some particular particles. And we also have temporal dependence. We have some advective term here, and we have some nonlinearity, which accounts for collisions and other kinds of interactions between the particles. Yeah. So if we took one-dimensional space, we would have one dimension, one spatial dimension, and one velocity dimension, and distribution function of a system, of one-dimensional system might be something like this. Yeah. So we know that we have a high probability of finding a particle at point x0 with velocity xi0, and rather low probability of finding it in point something like x star with velocity xi star. Okay, so this probability distribution function depends on multiple variables, not only on position in space, as for example, velocity and macroscopic approach would depend on, but also on particles' velocities. And this poses some problems with numerically solving the equation because we are dealing with multidimensional functions. So we have to not only discretize the problem in space, not only in time, but also in velocity spaces. So how would one do this? Let me briefly describe it to you now. As I said, to discretize this whole equation, we would have to choose some certain velocities, yeah, to be represented in computer memory. We would also have to choose certain points in physical space, yeah, to also be represented in a computer. And this gives would give rise to some kind of discretized Boltzmann transport equation. But how would one do it? Yeah, we have to take a step back in time and tell something about so-called lattice gas automata. What it is about. Briefly, if you are familiar with Conway's game of life, this is simply a grid. Yeah, we have a rectangular grid, and each point on the grid might be alive or might be dead. And the temporal evolution of this system, yeah, so the dependence whether in the subsequent step a given point will change its state or not depends on the state of its neighbors. Yeah. So for example, we might devise a rule that when a given node has 2 alive neighbors, it changes its state. Otherwise, it remains in its state for the subsequent iteration. So people came with an idea that let's apply this approach to molecular dynamics. Yeah. So for example, here we have hexagonal grid, and in each point of a grid, we might have or might not have one particle. Yeah. And now the subsequent iterations are based on 2 steps. First step is a transport of a given molecule that we know the velocity of to its neighboring cell. And when multiple molecules arrive at one cell, we must apply some collision rules to them. So for example, when 3 molecules with velocities like that arrive in one cell, at the end of the iteration, we have molecules with the same velocities in this cell. When we, for example, have one molecule moving with velocity to the left and other molecules standing still in a node, at the end of the iteration, they collide and bounce away from each other. Yeah, and then in the next streaming step, they arrive at some particular neighboring cells. And such an approach simulates fluid flow quite well. Here are some screens from master thesis of one of our faculty students. He was supervised by Professor Koza, as far as I remember, and those screens show application of such a model, yeah, such a lattice gas automata model, to simulating, for example, Kalman vortex street behind the cylinder or some microfluidic flow. Yeah, this upper screen is experimental result, lower screen is numerical result of Mr. Skoda. So it can be seen that that model is capable of like modeling real life fluid flow. But people came with such thinking even further and said, okay, let's replace Boolean approach to the description of whether a given cell might or might not contain a molecule. Yeah, so that would be 0 or 1, and deal with some real numbered values, which will represent the value of distribution function that will be stored in each cell. Yeah, so this extends the idea of lattice gas automata a little bit, but the regular spacing of the grid that lattice gas automata has allows for discretizing the velocities in Boltzmann transport equation. So it is done in a way that we have that grid and we know the value of distribution functions in each node. And now we say, okay, let's discretize only those velocities that correspond to the distances traveled by particles moving with those velocities from one cell to exactly its neighboring cell in a single time step. Yeah, so this is like a kind of Lagrangian approach that during each time step, we are concerned only with particles that can travel exactly the distance of grid separation in one time step. And here we have examples of velocity and space discretizations used in various lattice Boltzmann models. Yeah, so we might be concerned only with 8 nearest neighbors of a given node. We might be concerned with 27 nearest neighbors of a given node, but nothing stands in the way that one might also incorporate nodes lying further from a center node. Yeah. So going back to discretized version of Boltzmann transport equation, which, as a reminder, tells how the distribution function of a system evolves in time. The numerical procedure to solve it is as follows. First, we perform collision step. Yeah, so the collision step models interactions between particles. For example, collisions. Yeah, we have two particles, they collide, and after that, they might or might not change their directions and so on. So we perform in each of the nodes collision step, which changes distribution function in some way in those nodes. And then we perform streaming. Yeah. So the velocities of particles that we've obtained in a collision step are then a basis for transporting particles from one node to one of its neighbors. And once we do that, we repeat the collision step once again. We stream the particle populations once again, and that's how the procedure goes. All right, so I hope this wasn't too much. I hope this wasn't too hectic about numerically solving LB Boltzmann transport equation. And now let me go to some more pleasant part, I hope, of the presentation, namely to show you a few applications of this LBM method. Yeah, so Boltzmann transport equation was derived about in the beginning of 20th century, and it wasn't like until 1980s, late 1970s, when numerical approaches to solve it wasn't actually performed. Initially, people wanted to find out if this equation gives any might be possible to be accurately and properly solved numerically at all, and whether this equation possesses any unique solution at all. So in the beginning, there was a huge amount of mathematical work on the transport equation itself. Only in 1980s, 1990s, people started to implement LBM solvers. And the initial attempts weren't very spectacular, but well, that's what the beginnings are about. So people managed to simulate, for example, dimensions, Karman vortex street behind the cylinder. Yeah, so we have a cylinder here. We have a incident flow from, for example, its left, and at a given range of velocities, some kind of swirling whirlpools are shed in the wake of this cylinder. There were also early attempts of applying LBM to simulation of flow in porous media, and some later ones. This is work from 1996 to simulate flow in artificial valves that are inserted in human heart. Okay, going further now, let's take a look at porous media flows, applications of LBM. So Professor Matyka and Professor Koza are known for dealing with porous media simulations. Yeah, so this is a very big chunk of work, a very big chunk of application of LBM to fluid flows, to simulate flow in a volume that is heavily obstructed with obstacles. Yeah. Also, it is possible to use Lattice Boltzmann method to simulate porous media flow that deals with multiple phases. So here, for example, we are dealing not only with water, but also with air and decant. So it's like a 3-component flow, and it's I find it very very complicated and phenomenological. Another interesting like application of LBM to porous media that I found was using it to calculate the flow of protons through semi-permeable membrane. So basically there was that membrane that only protons could pass through, and we supplied it with hydrogen from one side, depleted the hydrogen of electron, which simply means that we separated electron from proton nucleus, and that proton nucleus was able to penetrate the membrane. The electrons had to go through some resistance in a circuit and come back on the other side of the membrane when the hydrogen recombined with oxygen to form water molecules. Yeah. Okay. So another application of LBM that I find interesting is simulating photocatalysis. So here simulation situation is kind of similar. We also have that semi-permeable membrane that only hydrogen atom nuclei can pass through, and applying sunlight, we deplete the hydrogen atoms of electrons. Hydrogen atoms go to the other side of the membrane, and there they are recombined with with electrons to form hydrogen atoms once again. Yeah, and Lattice Boltzmann method is convenient for such simulations in a way that it takes all those phenomena that go on here, this recombination of hydrogen nucleus, in a very convenient way through that collision operator omega that appeared on the right hand side of the equation. Yeah, so this is a very powerful tool, because if only we know a proper collision operator for the situation we want to model, we are basically ready to set up the problem and start simulating it. Okay, as I said, LBM is capable of modeling phenomena that rise from microscopic phenomena that take place in a system that is considered. So we might be we are not restricted to classical fluids like water molecules, with atoms, or air that is a mixture of some molecules, but we can also simulate particles that do not obey Maxwell-Boltzmann distributions. So for example, electrons. And here is an example of a work where guys simulated a electrical current, which might be considered as a flow of electrons between in a metal lattice that was obstructed with randomly selected obstacles. So this might correspond to some kind of impurities of a wire that is used in some electrical circuit. And once again, replacing the distribution function, some particular type of distribution function that appears in collision operator, allowed for accounting that we are simulating non-classical particles. Going further, also in microscale, there has been successful attempts of applying LBM to simulation of so-called crowded systems. And what they are about. Imagine a cell, or animal cell, or some other kind of cell, and for some reason we are interested in transport phenomena that occur inside of it. So perhaps you remember from biology classes in high school that the inside of cell is occupied by many, let's call them biological devices that allow the cell to function properly. For example, nucleus, some mitochondria to create energy, and so on and so on. But also that space between all those micro devices is occupied by proteins and other kind of objects that are of size far smaller than the one mentioned earlier. And the question is, does the diffusion and transport in such a system as an inside of a cell might be properly modeled by simple diffusion rules? And it turns out that the existence of those subscale obstacles might prevent diffusion and also transport of the concerned molecules severely. So once again, modifying the collision operator in Boltzmann transport equation might allow us to account for those micro particles, for those molecules that impair, that hinder the transport of some other concerned ones. Yeah, so let's take a look at those plots. This is a comparison between LBM and so-called crowded LBM, which makes use of that modified collision operator. And on the plots, there it is shown mean squared displacement of the concerned molecules against time. So one sees that for variable percentage of crowding of the system, so variable percentage of the number of proteins and all those micromolecules in spaces inside the cell, classical LBM predicts constant diffusion rates, constant diffusion coefficient for all percentages of crowding. On the other hand, that enhanced LBM method predicts, which is rather reasonable, that the more crowded the system is, the more hindered the diffusion of the concerned molecules gets. Okay, going further, or I might say very far away from Earth, LBM was also applied to simulating like stellar dynamics or extrastellar dynamics also. So on the left-hand side, you can see a snapshot of a simulation of galactic extrastellar matter flowing around, I'm sorry, some kind of interstellar cloud. Yeah. On the right-hand side, on the other hand, we have a temporal evolution of also relativistic rarefied gas when it comes to the formation of shockwaves. Yeah. So just to be brief, let's just take a look at the ranges of Knudsen numbers that this model is able to simulate. Okay, as I said, LBM inherited much from lattice gas automata, for example, regular grid spacing in all directions. But it turns out that this would not have to be the case if one uses, for example, interpolation procedure to calculate certain things in the course of the solution algorithm. And this allows for the usage of non-regular lattices. So here the approach is very simple. Instead of transporting molecules from neighboring cell to another neighboring cell, we might say, okay, let's transport particles from this cell. Yeah. How to do it? We have to interpolate distribution function between a number of neighbors of the wanted point to this point, and then make transport of those particles to the desired arrival point. Yeah, and this allows automatically for using unstructured grids, for variable discretization density, and so on and so on. So going to the end, I'd like to present a little bit of my simulations that I've so far managed to do during that first year. So I'm also interested in that off-grid LBM, that interpolation supplemented LBM. And for interpolation, I'm using radial basis functions. So these are basically functions that are symmetric, radially symmetric about their center. Yeah. And what's more important, they're capable of transforming multidimensional spaces into simple scalars. So like so far, I've managed to perform like successful, satisfactory simulations of lid-driven cavity. Note the variable density of the discretization from the center up to the very corners of the domain. Also, I've applied that off-grid approach to simulating fluid flow in porous media and randomly generated porous media. I did some analysis on the spatial convergence of the errors. So it is convergent, but in some very peculiar and non-trivial way. And further plans, at least for this moment, are utilizing that method for simulation of transport inside and between neurons and glial cells in living organisms' brains. So let's go to the summary. LBM is a numerical tool for solving lattice Boltzmann equation. Yeah, it accounts for discretization in time, in space, and in velocity space. In contrast to, for example, Navier-Stokes equation, Boltzmann transport equation takes mesoscopic approach, as I've described in the very beginning. This causes this equation to be solved for particles distributions from which macroscopic quantities like velocities, densities, and for example, pressures might be obtained rather than solving the equation for those microscopic variables directly. Okay, microscopic quantities are possible to be retrieved from the distribution function. And due to this ability of the model to account for microscale phenomena, it is convenient to extend the basic approach of LBM to some exotic situations of fluid flows, as we've seen. Yeah, and I'm sure that apart from those few slides of applications that I've shown today, there are many, many more, even more exotic applications of LBM. Okay, so let's call it a day at this point, and I will welcome any question and discussion on the topic.